All right. Good to go. Okay, everybody, welcome to another exciting day in algebra. Let me make an announcement. A couple of things first. Got a math club this Friday at 5 o'clock, and Marvin Jones is talking actually about visual cryptography. And I know there's a lot of people that might be interested in that kind of thing here, so I encourage you to do it. The idea comes from, I think this is a really interesting idea. You can basically decompose an image, and so you can have some things that look very grainy, you know, like maybe static on your TV, but if you overlay them properly, then it's something that you can discern visually. He's going to talk about that in multiple dimensions, so it should be a lot of fun. The course evaluations for this course will open on April 15th and be open for until May the 6th. If you guys like, I'll give an extra homework score if you work this out or do the evaluations. But please do the evaluations. They'll be open starting April 15th until May 6th, which is the last day of finals week. By the way, I think the default is they close on May 1st, but I actually changed that. So if you do evaluations in your other classes, you might have to do them earlier. And finally, I am on the schedule to teach Math 9500. Seriously. Julia, do you know that somebody's got control of this camera? Or do I have like competing? Okay, I declined you, but Julia, send me that. Oh, okay, I got you. I thought that there were actually people fighting over being the director. All right. The last thing is I'm on the schedule for teaching Math 9500 in the fall. It's commutative algebra. We're going to do some integrality, multiplicative ideal theory, multiplicative sets, localizations, things like this. It should be a fun course. I sent all the graduate students a syllabus. You can kind of get an idea. It'll be like this course. It'll be homework based. There'll probably be less homeworks than in this class, but it should be fun. So if you're interested or if you got any questions about it, let me know. Okay, so let me get to last time, and I've got a great sort of story here. If I can get to that this time. So the last time we talked about was this thing called right here. These are the roots of f of x, and I assume that the polynomial was separable. Actually, don't even need to assume that. And this is called the discriminant. And last time we discussed the result that says E is in ground field K, and if and only if the Galois group of F is a subgroup of Sn. I'm sorry, An. Right. So actually, let me point out that well, let's say for cubics over Q, this tells you what you need. And the reason is because if the f of x is irreducible of degree 3, then the Galois group of f is isomorphic to S3 or A. Right? Because it has to be a transitive subgroup of S3, and that's it, right? And so basically this result tells you everything you need to know, because if that delta, if the square root of the discriminant is the square root of the discriminant is in the base field, then that's the Galois group. And if the square root of the discriminant is not in the base field, then that's the Galois group. So basically that observation tells you everything you need to know about cubics. Let me go more in depth on this. So let's write the cubic polynomial. And let's assume that it's monic, because if it's truly cubic, then you can divide out by the leading term and just make yourself easier. Let me give you the discriminant here. This is a squared b squared minus 4b cubed minus 4a cubed c minus 27c squared plus 18a b c. Right. By the way, I just wrote that down for you. How would you figure out such a thing? Well, it's actually not terrible. I challenge you to figure this out, because this polynomial here in its splitting field should look like this. So that's what the polynomial should look like in its splitting field. And so from this, you've got enough information to derive to get this out. And how do you get it? Well, you know several pieces of information. You know that R1 plus R2 plus R3 is negative A, right? Because basically, when you look at minus R1 minus R2 minus R3, it is the coefficient of the squared term, right? You also have R1, all the possible two products of the added up is the coefficient of the linear term. So you get R1 R2 plus R1 R3 plus R2 R3 is B. And finally, you get R1 R2 R3 equals C. And what you have to do to compute the discriminant is figure out what this product is here. And if you use that in tandem with this information, you can get this. So it's an exercise. It's grungy, but you can work through it. So, for example, minus 1. Then discriminant actually is equal to 49. So in this particular example here, you get the discriminant is 49. By the way, as you might guess, I had to pick these numbers here. In this case, A is 1, B is -2, and C is -1. I had to pick these numbers carefully. Notice that so the Galois group of this polynomial is cyclic. Notice that if I pick random numbers A, B, and C, what do you suppose the chances are that this turns out to be the square of a rational number? Probably not, right? So you have to sort of carefully pick this to make this come out to be the Galois group to be Z3. But like I said, this discriminant tells you everything you need to know. It's either a square, in which case Galois group Z3 or A3, or it's not a square, in which case it's S3. Now, I'm going to go up to the next level, which is quartics. And how do you deal with quartics? Well, let me remind you that the transitive subgroups isomorphism classes of S4 are S4, A4. Yeah, I'll do this one. E4, dihedral on the square, cyclical 4, and this one that I'm going to call B. You've got that weird one that's, and notice it's kind of interesting because there are a number of Klein 4 subgroups of S4, but this is the only isomorphism. This one's different than, for example, if you just had 1, 2, 3, 4, and 1, 2, 3, 4, that's not transitive. So not all of the isomorphism classes are transitive. So this one is, and one way to deal with quartics is to sort of key on this group here. This subgroup, so here, what we're going to do is we're going to suppose that K is a field. And again, I'm going to assume the characteristic K. And we're going to let F be the splitting field of an irreducible quartic with distinct groups. An irreducible quartic over K with distinct roots in the splitting field. And I'm going to let G the Galois group of F, that is the Galois group of the splitting field F. I forgot to say that. So the Galois group of lowercase f is the Galois group of the splitting field polynomial, namely f. And you'll see why this why it's important the polynomial is separable, that is, has distinct roots here in a moment. So what I'm going to do is now let R1, R2, R3, R4 be the, and of course, the distinct roots of F. it's splitting to a capital F. Now, what I'm going to do is I'm going to pick these elements cleverly, I think cleverly. And you'll see there's a pattern that relates to this animal right here. So I'm going to define alpha. Make sure that I stick to my notation here. R1, R2. Beta, gamma. So beta is going to be R1, R3. Now, let me point out something. Notice that, how does V act on alpha, right? Well, notice the first element of V actually permutes 1 and 2 and 3 and 4. So this element acting on alpha leaves it alone, right? But what does it do to this one? Well, it takes 1 to 2 and 3 to 4. So this becomes a 3 and this becomes a 4. And this becomes a, am I doing this right? This becomes a 2 and 4. Right. So the second element takes, how does that act on beta? It takes 1 to 2, so this is R2, and it takes 3 to 4, so this is R4. So it goes to this, it takes 2 to 1 and 4 to 3. So notice the beta is fixed by that first element as well. What happens to gamma? Well, in gamma, 1 goes to 2, so this is R2, R3, which is this one, and it takes this guy back to this. So all of these are unaffected by the first one. 1, 3, 2, 4, for example, that'll clearly freeze this. 1, 3, 2, 4 takes, this goes to R3, R4, and that goes R1, R2, right? So these elements are all fixed by the elements of V. Everybody agree with that? That's why we set this up this way. So we're going to use this as a tool. Under Galois correspondence, the field K adjoined with alpha, beta, gamma. So you take your base field K and you adjoin those three things, corresponds as we've noticed, alpha, beta, and gamma are left alone by V. So this corresponds to V intersect G, which is normal G. So K, alpha, beta, gamma is Galois over K. And its Galois group alpha, beta, gamma over K is isomorphic to G mod V intersect. And that just follows right from the Galois correspondence, right? And like I said, we're not going to use this to kind of bootstrap our way and figuring out what the Galois group Proposition. Eight, 5, 7. Well, it can't be a field. And I'm going to define f to be the polynomial x4 plus ax cubed plus bx squared plus cx plus d. This is my Cubic polynomial. There's a cubic polynomial that we can associate to my original polynomial, the coordinate that we're trying to figure stuff out about. So we take our original coordinate and we're going to get a resolvent cubic, an associated cubic polynomial that sort of keys on this business that we've done here with these strange roots. This resolvent cubic is x cubed minus bx squared plus ac minus 4dx minus a squared d plus 4bd minus c squared. So this is resolvent cubic. Again, you can figure it out in a similar way that we figured out what the discriminant was for cubic. And let me tell you where this comes from. I mean, it looks like I just, whatever, drank a couple shots of bourbon and just started writing letters down. But where does this come from? This is actually x minus alpha, x minus beta, x minus gamma, where alpha and beta and gamma are these things over here. So you know that this field is Galois over the base field with Galois group G mod this right here. And so really, what you need to sort of go all the way up is you need to sort of see what happens in this polynomial here. Notice that any element of V fixes all alpha, beta, and gamma, but how do the other automorphisms work on it? So here is the theorem that sort of answers that. By the way, you might ask why I call this proposition. The only thing worth proving here is really that when you multiply this out, you get this. So I'll leave that as an exercise. Yeah, that's why I call it proposition. It may not have been so clear. Theorem. Okay, so here is actually a very practical thing, and I'll apply this theorem with a couple of examples. But it can be a field, and F I want this to be an irreducible coordinate. I guess I still want the characters not be two. With statements. in Springfield. And Galois group. That's 4. Let alpha, beta, and gamma be the roots of the result of the resolved cubic. That is so. And let M be the degree of this extension. Remember, this is Galois extension of K. M is this degree. Then we have the following. Number 1. M is 6. M is 3 if and only if yeah. So really think of it this way. Notice that M is 6 and the size of this group is 4. 6 times 4 is 24. That's essentially where that's coming from. When you do the Galois correspondence in the indices, that's why this is the case. M is 3, 6 times, I'm sorry, 3 times 4 is 12, which is 8, the size of A for. M is 1, Galois group is already, we've already got it. It's just the V. Notice that there are 5 transitive subgroups. I've got 2 left over and only one other possible divisor of 6. And so actually M equals 2, then I've got a choice, right? I've got to further discern. M is 2, if and only if E is isomorphic to C4 or D4. And how do I decide which it is? And G is isomorphic to D4. If and only if the polynomial F is irreducible over. Right. So if you get n equals 2, if you have m equals 2, then it sort of clips a subgroup of this in a certain sense. And if m equals 2, then what happens is you look at the original, you look at the polynomial f over this intermediate field. If it's irreducible, then you're stuck and you have to go up to the full 8. right? And if not, then it's cyclic of order 4. So let's look at some examples of this. And basically, again, this all follows just basically by counting and looking at the indices and the Galois correspondence. So let's look at a couple of polynomials just for fun. Let's look at these polynomials here. First, let's look at x4 Now, what I need to do here is I need to find alpha, beta, and gamma, right? Right. Let me recall for you that alpha and actually, I guess there's a number of ways to do that. Maybe what we can do is jump right to the resolvent cubic here. Because notice I can figure out the roots of all of these and just do it, right? Just do the substitution, u equal x squared, get the roots and take square roots of those. Then I have to figure all this out. Let me look at the resolvent cubic and see if it's easy. See if I still got that written up there. Of course I don't. So I'm gonna put this in. I'm gonna leave this up here in case it's useful for me next time. AC minus 4D. And I'm hoping the resolvent cubic will be easier because there's going to be a lot of stuff that's zero here. Minus a squared D. Minus c squared. So the resolvent cubic for this one should be x cubed. And we'll see here what we have is A is B is 4, C is 0, D correct. So here, what do we have? We have x cubed minus 4 a squared. Right. AC, which is big about 0, minus 4D minus 8x. And then what's this one here? A squared D, so that's going to be a 0. That's going to be a 16, I guess, and that's going to be a 0. Actually, it's more than that. 16, it's 32. Let's see here. That's going to be 16 plus 16. Okay. Oh yeah. Does anybody see a root of this? I do. I think it's got a root of x minus 4. 64 minus 64 minus 13. So let's see what's left over. It should be x squared. Squared. That's going to be minus 8. So that looks right. X cubed minus 4x squared minus 8x is 32, which is x minus 4, x plus 2 radical 2, x minus 2 radical 2. Now, in this case, actually, this work range field, if you look at K alpha beta gamma, well, no, actually I do want it for Q because it doesn't depend on whether radical 2 is there or not. This is adjoint 4, 2 radical 2, minus 2 radical 2. This is huge overkill. So in this case, n equals 2. Everybody agree with that? So n equals 2, I want the Galois group. Well, already I know it's C4D4. So the question is the original irreducible or is the original polynomial irreducible or not over this field? Let's see, 16 minus 4 is 8. Yeah, it's going to reduce, right? Because really, what this is notice x squared is equal to -4 plus or minus the square root of 16 minus 4 is 8 over 2, which is minus 2 plus or minus radical. So this polynomial, you can factor at least this far. Yep. So this first one has Galois group cyclic border forward because the polynomial reduces over that. Any questions? Okay, let's look at another one. Let's look at a couple more. How about this one? X4 minus 10x squared. Yeah. Minus 10x squared plus 4. Notice in this case, what we have is, in this case, what we have is A is 0, B is -10, C is 0, D is 4. And let's hope we get the result of the cubic right. X cubed plus 10x squared. Let's see, AC, that's a big fat 0, minus 4D is minus 16. And the last term, A is 0, B and D are not, C is 0. So it's going to be 4, BD is minus 40, so it's minus 160. Yeah, that's real convenient again. This is x squared times x plus 10 minus 16 times x plus 10, which is x squared minus 16 times x plus 10, which is x plus 4 minus 4 x plus 10. So if you look at Q, the join with minus 4, 4, and minus 10, this is Q. So the Galois group is big. Finally, let's do this one. There was a dog that wasn't Lester.
I know, I heard the tabs and I was like, oh, that's just coming out.
Okay, so let's do this one. Here we have A 0, B equals 0, C equals 0, and D equals -4. We know it's not -2. So now my resolving cubic is x cubed. Oh, there it is. X cubed, that's a 0. Let's see, minus 4dx. So that's going to be 8x. Right. And it's 0, and then 0. Right. Now, this polynomial is x times x squared plus 8. And so, which is x times x plus, see, this is 2 radical 2 I x minus 2 radical 2. So we get Q alpha beta gamma is Q adjoined with 0, 2 radical 2 I, and 2 minus 2 radical 2 I. Now notice this is just redundant because any field that contains 2 radical 2 I also contains its conjugate, right? So this is just really, which is actually Q I radical 2. That 2 is redundant as well. Now, the degree of this is, this is also degree 2. So once again, we have to make a choice between, the dihedral group or cyclic group. And this is going to be dihedral, I think. Because if you look at the original polynomial, say 4. This has plus or minus here. Yeah, it's minus. So the roots of this two minus 2 to 1 4 and minus 2 to 1 4. And so x to the 4 uh, Right. And if you piece these back together, so the question is can you put these factors together so that notice that none of these linear polynomials are in here, right? Because you need a fourth root too, right? So the only way that this could break down over that is if a product, if either this product or one of these products here actually had all its coefficients in 2 radical 2i. So if you multiply this times this, it doesn't work because the product of these two is x squared minus 2 to the 1/2. And 2 to the 1/2 is not in here because it's stuck to that I. You've got the same problem multiplying these two here. Now, what happens if you multiply this here? Well, the problem here is the constant term and the leading term are okay because the constant term will be 2 to the 1/2 I. But you get this middle term that is 2 to the 1/4 minus 2 to the 1/4 I. And so in other words, you cannot piece this back together so the two quadratic factors are in here. So it's D4 on this one. Okay, any questions on that? Okay, I have just enough time to give you, so this is very specific. This is, for cubics and quartics over a field characteristic not 2. You can figure out the Galois group. Let me give you sort of a neat theorem that helps you eliminate things, and then I'll give you kind of an apocryphal story next time, and then maybe another. So here's this theorem that I want to throw at you. Theorem 8.5.10. Suppose f of x is monic polynomial of degree n. In Zx. It's polynomial with integer coefficients. And if it's rational, you can, well, I guess you'll have problems going to monic. Actually, it doesn't really need to be monic. You just, I'll correct that in a moment here. Let P be any prime number in Z. We also suppose f of x n distinct roots. And splitting field, well, R of x. Think your polynomial reducible mod P, and we're going to assume it has indistinct roots in the splitting field. The splitting field is that large. Right. So for example, an Eisenstein polynomial wouldn't work very well here because an Eisenstein polynomial will just give you an x to the n power. Then if that, well, Eisenstein over that particular problem would work well. If f of x factors so factor mod P f of x as G1 x, G2 x, Gp x. And the good thing about that is there's only finitely many ways you can factor it, so you can certainly exhaust these possibilities on the ZP. with the degree of each GI at equal to MI. Then there's an element of the Galois group. There's this element of Galois group F. And I do mean the original F over Q of the form C1, C2, CK, where each CI is a cycle of length MI. So in other words, let's suppose, just for the sake of argument, that you have a degree 5 polynomial, right? And let's suppose that you find a prime P, and mod P, that breaks down into an irreducible cubic times an irreducible. And here I'm assuming, when I say a factor, these are irreducible polynomials, right? Suppose that it factors into a cubic times a quadratic, right? That means that in the Galois group of the original polynomial, there's something that looks like a 3 cycle times a 2 cycle, right? And actually, for that particular example, that'll tell you exactly what the Galois group is, right? Of the 5, there's only one transitive subgroup of S5 that contains an element that looks like a product of a 3 cycle and a 2 cycle. So we'll talk more about that next time. Any questions out there or in here? Okay, well, you all have a good one, and we will catch you on the flip side.